All right, I'm Hoyt Brignac. I'm your Toastmaster for today. We'll have 3 presentations. And up first, we're going to have Zilin Li on vapor compression refrigeration lab 3.
So good afternoon. I'm Zilin Li, the group reporter for Lab 3D refrigeration cycle for heat pump. So this is the basic setup in the lab. At the top center, there's a compressor. At the left-hand side, there's a condenser. Right-hand side is the evaporator. There's an expansion wave connect between the condenser and evaporator. At the very bottom, there's a water tank. The water flow is pumped to the condenser by the water compressor right here to heat exchange with the condenser and evaporator. So the water absorbs the heat from the condenser, which is the QH, and the water dissipates the heat to the evaporator, which is the QL. The reason why there's a water tank here is to quantify both the QH and QL. As we know, the water is compressed liquid, so we could use Q equal to C and delta T to calculate the QH and QL. The delta T is the temperature difference in both the inlet outlet for both the condenser and evaporator. So this is a page diagram for the refrigeration cycle, and I will go through that step by step. So from process 1 to 2, the compressor compressed the fluid from saturated region to superheated vapor, and this process is assumed to be adiabatic and isentropic. And from 2 to 3, the condenser condense the heat, which is the QH, out to the ambient. So the fluid from superheated state back to the saturated region, and the process is assumed to be isobatic. From 3 to 4, the fluid will go through expansion valve, and the process is assumed to be adiabatic. So stage 3 and 4 has the same enthalpy, and from 4 to 1, the fluid will go through the evaporator to absorb the heat from the ambient, which is the QL, so that the enthalpy for the fluid increases back to state 1. And this process is assumed to be isobaric and isothermal. And next is about the COP for the refrigeration cycle. Because this system is designed to be a heat pump, so the COP is represented by a beta equal to QH divided by the compressor work. So in other words, something what we want is divided by something we input to the system. So we want a QH, and something we input to the system is the work from the compressor. And we could, and in ideal cases, the COP can be simplified further into TH divided by the difference between TH and TL. The TH is the ambient temperature around the condenser, and the TL is the ambient temperature around the evaporator. And this one is thermostatic expansion valve. And there are 3 important pressures to interact together to control whether the valve is opening or not. So if the so-called pump pressure is greater than the sum of both the spring pressure and external evaporator pressure, then the valve will open so that the flow can flow from the condenser through the evaporator. This is the experiment data. This is a case 1. In order to identify data, I put red color as something that I either calculate from the equation or the integration from the appendix table. And for the black data is something that our group collect from the lab. The green data, there's just one green data, is the changing variable. It's called the evaporator heat exchanger. It should be a volumetric flow rate. The green data is different in each cases. In this case, it's 6 liters per minute. So in order to draw the pitch diagram, we have to find out the enthalpy for state 1 to 4. And 5, 6, 7, 8 is just the water temperature for a heat exchanger. And we don't have to worry about the pressure and enthalpy for 5 through 8. So from 1 to 3, we collect the temperature and pressure from the lab, so it's easy to find out the enthalpy from the appendix table by interpolation. And based on the assumption that for stage 3 and 4, they have the same enthalpy, so go back to the appendix table, we could find out the pressure for stage 4. So we got all the information, so we can grab the pitch diagram. And I put an ideal case to compare with the real cases. And finally, we figure out the COP is around, this is case 2. Could you go back? Yeah, the case 1, the COP is around 3.88. And the same procedure, but the difference is the evaporator heat exchanger volumetric flow rate is 4.5 liters per minute right now. And if we follow the same procedure, we could get the COP is 4.33. The last case, the evaporator heat exchange volumetric flow rate is 3 liters per minute, and the COP is around 12.67. As we can see, if we're decreasing the volumetric flow rate for the evaporator side heat exchanger, the COP is increasing. Lastly, I want to talk about some uncertainty. The first one, the uncertainty comes from the measurement devices. The second one, there will be energy loss by friction and mechanical vibration inside the compressor. Lastly, the volumetric flow rate inside the heat exchanger for both the condenser and the evaporator is not necessarily a constant.